Hello, good evening everyone. Manisa, can you hear me?
Yes, I can.
Good evening. Welcome to the third international workshop, Initiation to Linear Algebra. Speaker of today's session, Dr. Sumesh K, Assistant Professor, IIT Madras. And topic, Spectral Theorem for Complex Normal Operators. It's my great pleasure to introduce and welcome our speaker, Dr. Sumesh K. He is currently working in the Department of Mathematics as Assistant Professor, IIT Madras. He was a postdoctoral fellow at the Institute of Mathematical Science, Chennai, a senior research fellow at the Indian Statistical Institute, Bangalore, and a junior research fellow at the Indian Statistical Institute, Bangalore. He has 6 published research articles. His area of research in function analysis and his research interests are mainly in the theory of operator algebra, especially focusing on the theory of completely positive maps, completely bounded maps, quantum dynamical semigroups, product system, dilations, representation of C-star algebra and Hilbert C-star modules, and also research interest in the theory of quantum information. On behalf of the Department of Mathematics and Organizing Committee, I extend a very hearty welcome you, sir. I cordially welcome Dr. Varghese Matthew, our principal, Professor Minnie Thomas, head of the department. I also extend a very warm welcome to all the participants. Let's start our today's session on Spectral Theorem for Complex Normal Operators. Over to you, sir.
Okay, thank you. Hope you can see my screen.
Yes, sir.
Good evening, all of you. So this is the third lecture of this online workshop. So first of all, let me thank the organizers for the invitation. It's my great pleasure to be a part of this online workshop. So this is actually a continuation of the first 2 lectures. So the topic or the presentation I organized in the following way. So I'll start with some of the notation that I'll be using throughout the lecture, and then I'll recall some of the result and basic definition and notation which we used in the last 2 lectures, and that will be, I'll be using those things in today's lecture. And then I'll slowly build up the tools for proving the spectral theorem. And then finally, towards the end, if time permits, I'll provide some examples and also give some immediate consequence of spectral theorem. So let me see, we'll get time for all these things. Okay, so here today's talk is on a spectral theorem for normal operators. So here I mentioned that it's finite dimensional. So from here itself, it's clear that there is also an infinite dimensional version also. But that need some more tools to prove the spectral theorem, and you have to be a bit careful also when you prove those things. So in the finite dimensional setup, you have 2 things. One is that you might have already seen that whenever you have a linear map, you have an associated matrix. So this theory, so when you look at the finite dimensional case, you have 2 analog here. One, you can prove the theorem in terms of the matrices, the spectral theorem for matrices, and another one is spectral theorem for linear maps. But most of the time, you can see that we'll be using spectral theorem for matrices very often than the spectral theorem for normal operators. So what I'll do is that I'll prove spectral theorem for matrices first. Then from that, I'll derive or I'll just deduce a spectral theorem for normal operators. Okay, so this is what I want to say. Okay, so let me just start with some of the notations. So this is what, so C means this field of all complex numbers. So in the last 2 lectures, you might have seen that C2 generally the elements of Cn, we write it as row vectors, but I prefer to write them as column vectors. There's nothing, there's no difference, everything is fine, just it's a matter of convenience whether you want to write it as a row vector or a column vector, but I prefer to have it as a column vector. Okay, now suppose you are given 2 vectors x and y. Then in the last class, you defined the inner product. So how it is defined? Inner product of xy is defined as summation j equal to 1 to n xj yj bar. And you know that some of the properties is inner product status. So you don't want to use the details today. Okay. Now suppose I start with two matrices A and B. So by this I mean A is a n by n matrix whose ijth entry is equal to Aij, and similarly for B. Okay. Then when you are given two matrices, you know how to multiply them. So how we multiply them? So let me just wrote the matrix in bigger shape. So here, look at the product of A and B. So I am interested in the product and how we get this product. So let us look. I want to just see what is the first column of the matrix, how we obtain. So look at the first entry. The first entry obtained by just multiplying the first row and the first column. That gives the first entry. And how we get the second entry in the product? I look at the second row of A and again the first column of B. That gives me the second. And so and so. If I look at the last row and the first column of B, that gives the last n1th entry of the product. And similarly for the other column. So essentially how we got, so if you just look at the first column, how we got this one? You multiply all the rows with the first column. That means essentially you are multiplying the entire matrix A with the column vector, this first column vector. So in other words, if I write the matrix B equal to B1, B2, etc. Bn. So this again a notation. For convenience, I write this way. But this B1 means the first column and B2 means the second column. So when I write this red color, this bar means I'm just separating the column. So when I write this way, that means they are the columns. Okay, so how we get the product? The first column of the product is essentially you multiply the matrix A with the first column. And similarly, the second column, you can see that again you obtain by multiplying the matrix A with the second column and so and so. Okay, so this we'll use this notation very frequently in this lecture. So just keep in mind this one. Okay, now once you are given a matrix, there's another associated matrix, namely A star. All of you know what is A star. So how you define the matrix A star? Just look at the matrix A and look at the conjugate of all the entries, then you take the transpose. So that what A star means. Okay. Now, once I given two matrix A and A star, you can ask whether the matrix A is same as A star or whether this A and A star have some properties. So depending upon this one, you can classify the matrix A. So namely, I will say that the matrix A is said to be self-adjoint or Hermitian if A is equal to A star. That means A and A star coincide. And I will say that is a normal matrix if A star A is equal to A star. That means what? A and A star commutes. And we'll say that it's a unitary if A star A is equal to identity. But so look at the matrix here. So here it is actually the size of the matrix. This is a square matrix. So this condition is in fact equivalent to this one also. A star is equal to identity. But in general, if I have an arbitrary matrix, these two conditions are not equivalent. But when you are in a square matrix, these two conditions are equivalent. So this is what I know call it as. Whenever this condition holds, then we will say that the matrix A is a unitary matrix. Now I will say that the given matrix is an orthogonal projection. If A is equal to A star, that means A and A star coincide. And also when I look at the square of the matrix A, that is same as A itself. Okay. So now look at the definition. So this saying that if I look at a self-adjoint matrix, that means A equal to A star. Then if A is equal to A star, it is automatically clear that A star A is equal to A. That means all self-adjoint matrices are normal. And if I look at unitary matrix, so this A star A is equal to identity, and that is also equal to A star. That means A star is equal to A star A equal to identity. That means again A and A star come. That means what? Unitary matrix also normal matrix. But that is not the case with orthogonal projection. Okay. So this what keep in mind these are definitions. Okay. Now one small thing. This is an exercise. This is a very basic exercise which we will be using this result very frequently. But I want to say that suppose you start with the matrix U. So I am writing as U, and this is U1, U2. So by this I mean you will say a matrix with the U1 as the first column, U2 as the second column, extra UN as the last column. So each UA is a column vector from the CA. Then you can prove that this matrix U is a unitary if and only if the columns, the vector un. So remember that each ui is an element from Cn. So you have n elements in Cn. So you can see that this matrix U is a unitary if these vectors form a orthonormal basis. So remember that what we mean by orthonormal basis. So that means it's a basis. It's not just that's a basis. When you look at the inner product of ui with the uj, that will be equal to 1 when I equal to j and equal to 0 when I not equal to j. Okay. So this is very easy. This is nothing to worry. So what you have to do is that I have to prove that U star U is equal to identity if and only this is an orthonormal basis. Okay. But okay, let me write. If I look at the vector U1, U1 is an element from C. So I can write it U1 as a column vector, say U11, U21, U31, etc., UN1. And similarly, you write all the vectors. U2 is equal to U2, U12, U22, etc., UN2. And similarly, you write all the vectors. Then you multiply, then you can construct U star. Then you know how to multiply the matrix. That means you can compute the U star U. Then you verify that. When you just compute U star U, you can see that the ijth entry of the product U star U will be equal to inner product of uj with the ui. Then what happens? If U star U is identity, so you have only the diagonal elements in the product and all other elements will be 0. That means what? But what is the ijth entry? Ijth entry uji. So on the diagonal elements entry, so on the diagonals you will get elements uj, but that is equal to 1. That means uj has norm 1. But if I look at j not equal to I, that means we are getting off diagonal elements. But that we already saw that if U star is identity, all other things are 0, off diagonal things. That means uj ui is equal to 0. And the other way also equal. So this is a nothing, is just a matrix computation. Okay, you just convince yourself by just looking at the multiplication. Okay, so this again, I said that we will be using this result very frequently. Okay, now let me just recall some of the things that you did in the last class. Okay, so to begin with, let me just throughout the lecture, we always denote a finite dimensional complex inner product space. So this is very important. I'm only looking at complex inner product space. That means vector spaces over complex field. I'm not considering real vector spaces today. Okay, now we know that the notion of basis. Now, so let us start with the basis. V equal to V1, V2, etc. Vn is an ordered basis. Okay, so what I mean by order? So order means I'm fixing the order of the basis. That means what is the first element, what is the second element, and what is the last element, like that. So this order matters for me. Okay. So whenever I change the order, that I consider as a different order. For example, if I write V2, V1, V3, etc., Vn, that will be another ordered basis. Okay, so the order is important here for me. Okay. Now, once you are given a basis, what do you mean by a basis? That means if I given any vector in the vector space, I can always write it as a linear combination of this basis vector. That means what? Given any vector V, there exists unique scalars a1, a2, etc. an from the complex field, such that the given vector V, I can write it as a linear combination of v1, a2, etc. Vn. That means what? Given any vector V, I have numbers a1, a2, etc. an. So I can think of this as a tuple. And if you write it as a tuple as a column vector, namely, I'll consider this one, a1, a2, etc. an. So remember that. This is why I mentioned I need this to be ordered. So this a1 stands for the coefficient corresponding to v1, a2 stands for the coefficient corresponding to v2. So if I change the order of the basis, I have to change the column vector also correspondingly. Okay, so the order is important, that's why. Okay, so this vector I call it as a coordinate vector of V with respect to the basis B. Okay, so that means that's just the coefficients of the expansion in the this basic expansion. Okay, so once you are given such a things, what you can do? Okay, so for example, let me just look at a particular case. For example, consider V equal to Cn, the n copies of C. Then you start any vector x in Cn. Okay, so for example, x equal to x1, x2, etc., xn. And you have the standard basis there. Okay, so let me take V is equal to the standard basis. That means what? E1, E2, etc., n. That is my standard basis. E1 means what? The vector 1, 0, 0, 0. E2 is 0, 1, 0, 0, 0. So now if I given any vector x equal to x1, x2, etc., the column vector x1, x2, etc., xn, that I can write it as x1 into E1 plus x2 into e2 plus etc. xn into en. So if I look at the coordinate vector of x with respect to the standard basis, what I'll get? I'll get exactly the same vector x1, x2, etc. xn. That means what? So in Cn, Cn, if I start with any vector x, and if I look at the coordinate vector of the vector x with respect to the standard basis, we get the same vector. Okay, that's you keep in mind. That will be using later. Okay, so there is a slight problem, not problem, slight difficult here in the sense that it's not very easy most of the time to get to the coordinate vectors. How I get this coefficient? But you are in a inner product space. Then what we saw yesterday that whenever you have a basis, you can do the Gram-Schmidt process so that you will get an orthonormal basis. Once you have an orthonormal basis, things are very easy in the sense that, so this is a orthonormal basis means in particular this is a basis. That means what? The given vector again, we can write it as a linear combination of u1, u2, etc., un. But if you know that the basis is orthonormal basis, what you know is that you can easily compute the coefficient a1, a2, etc. So actually given by the inner product v with the u1, v with the u2, etc., v with the un. So this one advantage of having an orthonormal basis. You can easily compute the coordinate vector. Okay, so this is all about the coordinate vector. Okay, now suppose instead of one basis, let me start with the two bases. So one is b, another one I denoted by b dash. So both are ordered basis for b. Now let me look at a linear map T. So this is a map from v to v. Then in the last lecture, you saw that given any linear map T, we can always associate T with a matrix. So that depends upon the basis. Okay. So that this is the notation that we use. Okay. So we have to be little careful here. So in the first space, I given the basis B. In the second space B, I'm considering B with the second basis B dash. Okay. Then I want to compute a matrix of T with respect to the basis B and B dash. But I'm writing the other order. Order here is slightly. So here B dash stands for the base for the second vector space and B for the first one. Okay, so this the order you just keep in mind. Okay, so how this matrix is defined? So remember that in the last lecture you already did. So how we compute this one? You just look at the first vector V1. Then you look at the image of V1 under the map of T. Then you expand the vector in terms of the second basis B dash. Okay, so you look at the T of V1, you look at the image and expand in terms of the basis B dash. Then you look at the corresponding coefficient and that you write it as the first column. So that is the first column of this matrix. Now but what is this exactly? So what you did is that you look at the vector T of V1, then you expand in terms of the basis B dash and you look at the this coordinate, this coefficient AI. But that is exactly, by our notation, that is exactly the coordinate vector of T of V1 with respect to the basis B dash. Okay. Now similarly, what about the second column? Second column you obtain by looking at the T of V2. You expand in the, so this W1, W2, etc., Wn is the basis. So you expand this in terms of this basis. Look at the coefficient, you write it as the second column. But again, this is what exactly by using our notation, this means that this coefficient exactly represent the coordinate vector of T of V2 with respect to the basis B dash. Okay, so this is your second column. So similarly, you can look at all other columns and finally you get the nth column of this matrix. That will be the coordinate vector of T of Vn with B dash. Okay, so this finally this is what you got. Okay, so remember that this is a column vector, this is a column vector, this is a column vector. Okay, so this you keep in mind. Okay. Now, one of the property of this matrix is the following. Okay, so for example, let me consider both the bases are the same. That means here B equal to B dash. Then we get the map T with respect to BP. This is what we get. Okay, that whenever both the bases are same, we'll simply use the one B here. Okay, we don't use 2B here. For the simplification, we'll only use TB. Then what I know is that given any matrix, linear map T, we have an associated matrix, namely TB. Now this matrix TB has some property. This is one of the defining property of this matrix. So you can see that if I look at any vector V, and if I look at the image of T of V, that is again a vector in V. So you can look at the coordinate vector of this T of V with respect to V. You can see that that can be obtained from this matrix multiplied with the coordinate vector of V. So this is an easy computation. There is nothing. You write V is equal to a linear combination of VI's. This basis vector VI's. Then you use the definition of TV, and then finally you compute the coordinate vector of this one. You can validate everything matches. Okay. So this actually, you can see that this matrix is the unique matrix satisfying this equation. Okay. So this is true for all vectors V. Okay. So what do we have? So again, in the last lecture, you saw that this map is actually a bijective map. So what do you mean by bijective? So you know that given any map, once you fix this basis, then given a linear map T, there is a unique matrix which is given by this way. And similarly, if I start with any matrix here, you can see that with respect to that matrix, you can associate a linear map here, whose matrix is exactly the matrix that you started with. So in that sense, this is actually a bijective map. And in fact, we have something more property for this map. So what you can see that, let us look at a scalar multiple of a linear map. So A is a scalar. Then you can look at the matrix associated with this scalar multiple. And in the last lecture, you saw that this actually is equal to the scalar multiple of the corresponding matrices. Similarly, if I look at sum of two linear operators, then I can look at the matrix associated with S plus D. That will be the sum of the matrices. And there is one more thing you can see. There are some more things you can easily verify. Instead of sum, you can look at the composition. So this composition, you can think of it as a multiplication in L of V. So if I look at this composition, again, this is again a linear map. So the matrix of this composition, you can see that is equal to the product of the corresponding matrices. So in particular, if I start with the S is equal to T, then what you get? T composite T. So that will get denoted by T square. So T square has the associated matrix norm T into the matrix T into matrix T. That means the matrix of T, the square. So in general, if I look at power of T, that means you take T k times composition. Then if I look at the matrix of that operator, you can see that is actually equal to the power of the associated matrix. Okay. So this is saying that whenever you are looking at the scalar multiple or a sum or a conversion or a power, whatever be it, the corresponding matrix also has the same property. Okay. What else you can have? You can have something more here. That is also important. So for example, you just start with the vector V and a scalar lambda. And suppose this satisfies this condition. T of V is equal to lambda V. Okay. Then you just look at the matrix TB with respect to and into the coordinate vector VB. So what we saw from here is that this is equal to the coordinate vector of T of V. Now, but what is T of V? By definition, you assume that T of V is equal to lambda V. So this tells me that T of V is equal to the coordinate vector of lambda V with respect to V. But again, that you can easily verify that the coordinate vector will be equal to lambda into the coordinate vector of V. So what this tells you? So this saying that suppose V is a non-zero vector, then what is this saying? V is a eigenvector of T with respect to the eigenvalue corresponding to the eigenvalue lambda. Then what is this saying that? So if you look at the matrix, this into this column vector is equal to lambda into again the column vector. So if I call this matrix as A, this as a column vector say X. So this saying that AX is equal to lambda X. So what that means again? You can see that if V is non-zero, the coordinate vector is also non-zero. So you can see that lambda is an eigenvalue of the associated matrix with the associated coordinate vector as an eigenvector. So this is saying that the eigenvalues of the linear map and the matrix also are the same. So what all these things tells you? So in the last class, again you saw that. Look at the linear maps on V. This actually gives you a vector space. Okay. And also you know that MNC, the set of all matrix spaces, that also form a vector spaces. Now what does this map tells you? This tells me that if I look at a scalar multiple or an addition of linear map, that correspond to a scalar multiple and addition here. In other words, this Phoebe is an isomorphism because it's already a bijective, and this first and second property tells you that this Phoebe is a linear map. So there is a bijective linear map. That means it's an isomorphism. So this tells you that to study the linear maps on vector spaces, finite-dimensional vector spaces, it's enough to look at the space of all matrices. and because all the properties are preserved here. Okay. So now let us look at a particular case here. Okay. Suppose I want to study a linear map T. So that this tells me that you fix a basis B, then you look at the associated matrix of T with respect to that basis. Then the eigenvalues, all the powers, everything is preserved. But there's a small problem here. Not problem, it's a small difficulty here. When you look at addition, things are fine. You know how to add matrices. But when you look at the power, T to the power K, what is, if you want to study T to the power K, what you have to do is that you have to study the power of the associated matrix. But how I multiply this matrix? There is a slight difficulty in the sense that suppose you are in a 100-dimensional vector space. Then what you get here is that the matrix of T will be a 100 by 100 size matrix. Suppose I want to look at the T to the power 1000. Then what I have to do? I have to look at the 100 by 100 size matrix, and I have to look at the 1000th power of the associated matrix. But then this is not easy. Even I said that to study linear maps, it is enough to look at matrices. When you come to the multiplication, things are not very easy, because if the size of the matrix is difficult, higher and higher, bigger, then look at the higher powers, it's not easy to compute the product. No. So what you need here is that, this saying that given any basis, I can always get an associated matrix. So what you consider, if you want to have this multiplication symbol, what I need is that this matrix with respect to this B has to be a single matrix, so that the multiplication will be easy. For example, so if I multiply two matrices, and if I know that most of the entries are 0, then the multiplication also becomes simple in the sense that most of the entries become 0, so that the multiplication becomes simple. So what you need is that I have to choose the basis B in such a way that the matrix of T, associated matrix T, has more number of zeros. Okay, so that's what I need to do. So this is the question. So suppose I fix a linear map T. So can I get a nice basis of B such that the matrix of T is single? So here, by symbol I mean I need to have more zeros in the matrix. Okay. So how will I do this work? So this is what we are going to answer in this lecture. So is it possible that I can always get a nice basis so that the matrix will be a single one? Okay, so to begin with, let me just say one thing. So we know that we are in a fine-dimensional vector space. So we know that it always has a basis. In particular, it always has an orthogonal basis. So you can always get a basis so that you can get an associated matrix of the linear map. But the question is that, can I get a nice basis? That's the problem. Now, if I have to answer this question, what you'll do is that suppose I have two bases and two associated matrices, how these matrices are associated. If I know that there are some relation, then that helps you in many ways. Okay, so let us try to answer that question first. So this is known as the change of basis. So what I do is that, suppose you start with the two bases and you have a linear map, then I can compute the matrix of T with respect to one basis B dash. So how I compute this one? In both the place I am considering B dash and B dash. Okay. Now, how I compute this second matrix T with respect to B? In both the vector space, I consider the same basis B and B. So this theorem says that if I look at the matrix of T with respect to these two bases, they are related. They cannot be arbitrary. They are related in this equation, by this equation. So what is U? U is the matrix of the identity map with respect to the basis B and B dash. So this identity represents the identity map. So remember that U is the identity map, and we are considering the basis B dash. So you have to look at the order will be changed. So first place you have to consider the domain place, you have to consider B dash, and in the codomain place you have to consider B. So that is what I get B dash. Okay. So how I prove this one? Okay. So I just sketch the proof. So we are given two bases. Now, what I know is that, just look at this one. So, identity B dash with respect to B. So, remember that whenever you have a T here and a V here, then the matrix T into V is equal to T of V, the coordinate vector of T of V. But what is T of V? In place of T, I have identity. So, identity of V. So, that gives me V. So, this is true for all V. Now, I am taking U is equal to this matrix. Okay. This already mentioned that that's our matrix U. Okay. Now, let us try to compute the matrix of T with respect to B. So how I compute this one? We look at the elements in B and look at the image under T, and then again you try to expand the image under the basis vectors of B. Okay. So the first column will be T of V1 with respect to the basis B. Again the coordinate vector of T of V2 with respect to B, and so and so. But what about this one? So from here, this what you're saying that given any V, the coordinate vector of V with respect to the basis B is equal to this matrix B. But this matrix we already wrote it as U. So that means U into V with respect to V dash. Okay. So now instead of V, we are taking T of V1. So from here, what we get that T of V1 with respect to B, the coordinate B will be equal to U into coordinate vector of T of V1 with respect to B dash. Similarly, T of V2 will be U into coordinate vector of T of V2 with respect to B dash, and so and so. Okay. Now look at this T of V1 with respect to B dash. Again, we saw that this is equal to the matrix of T into the coordinate vector of V1, and that is what we get here. And similarly, T of V2 equal to matrix of T into the coordinate vector of V2, and so and so. Now what you got here, you have U is a matrix, B is a matrix, and this is a column vector. So this is a matrix in the column vector. Again the same matrix into another column vector, and same matrix again into another. So what you have is that here, if I call this entire thing A into B1, A into B2, A into BA. No, so we saw that is equal to A into B1, B2, etc. BA. That's how we define the matrix multiplication. But what is this one? If I look at this one, you can easily see that this is actually the coordinate, the matrix of identity map with respect to the basis B dash and B. Okay, that's what the second, this matrix, third matrix you get. Okay, now look at this one. So you have identity matrix, identity map. You have two bases B dash and B, and you have identity map. You look at the matrix of T with respect to the basis, but the order is changed, B and B dash. What you can see that this will be equal to identity of B dash with B dash. The matrix of identity with respect to B dash, and that is equal to identity matrix. That you can easily verify. In fact, you can have it in general case. Suppose I have a map S here, and I have a T here, linear map, then the matrix of S into matrix of T will be equal to matrix of ST. And there is to be this matrix, this basis has to be very compatible. Okay. So that means what? So this is my U. So you have a matrix here, and that matrix into U is the identity matrix. And here everything is a square matrix. That means what? This is the inverse of this matrix. That means what? This is equal to the U inverse. So what you saw is that matrix of T with respect to B is equal to U into matrix of T with respect to B dash in U dash. And that is exactly what you need to prove. Okay. So this is saying that if I have a linear map and if you have two bases, the matrices are not arbitrary. They are related by this equation. Okay, now let us come back. So what is our A? So this is our ultimate A. So you are given a linear map T. Now I said that we can always get a basis. No, you are in the finite setup, so you can always get a basis. So let us fix one basis, say B. And look at the matrix of T with respect to this basis B. That means I'm both the place, domain and codomain place, I'm associating the same basis B. So let us call this is the matrix A. Now what is our aim? So this matrix A may or may not be single. So our aim is to get another ordered basis B dash such that the matrix of T with respect to this B dash is single. Okay, but what is that? So you have already a basis B, and now you have to get another basis B dash so that this matrix is single. But what we just found that these two matrices are related by this equation. They cannot be arbitrary. So for some invertible matrix U. Okay. Now what is our aim? So I want to get this matrix is a symbol way. So that this matrix is symbol. That means what? Equivalently, this has to be a symbol matrix. So this is what I need. Okay. So we have to saying that this is symbol if and only if this is symbol. Okay. But what is this? Okay, remember that this is equal to A. That's what I said, U inverse AU. So let us say that this U inverse AU, this is a product of matrix, that is some matrix. So let me call this is equal to D. Okay. If the product is D, then U inverse AU is equal to D. That implies that A is equal to UD inverse. So what I need to get is that to get a basis B dash such that this matrix is symbol is equivalent to saying that you have to get an invertible matrix U such that this is symbol. Or equivalently, I have to write the matrix A as a product like this, where the matrix D is a symbol matrix. So this is our A. So finally, the problem of linear maps, we prove that this is equivalent to the problem of matrices. So this is our ultimate aim. So we are given a matrix here. What you have to do is that you have to get an invertible matrix U such that U inverse AU is a simple matrix. In other words, this happens. Okay. So for example, I said that we want to have the basis in such a way that this has more number of zeros. So for example, if this is a diagonal matrix, okay, so T matrix of T with respect to B dash is a diagonal matrix. So what does that mean? That means this matrix is the diagonal matrix. No, because this is equal to this one. Both are the same. So that means this is diagonal means this is a diagonal. Or if this matrix is some other matrix, for example, it's an upper triangular matrix, that means what? This is again an upper triangular matrix. So what I need to prove that to get a basis B dash such that whether this matrix is a diagonal or upper triangular or some other matrix is equal to proving that given any matrix here, you have to get a matrix U and a symbol matrix D, whether it is a diagonal or upper triangular, such that A is equal to U inverse. Okay, so this is our A. But one more thing. So we are in a product space. So what I prefer to have is that just basis is not enough for me, because I would have even a better. I would not have an orthonormal basis. So that will resemble that. In this setup, it tells me that instead of invertible matrix, I would like to get a unitary matrix. So I'm even asking a strong question. So is it true that given any matrix here, can we get a unitary U so that this U star U is a simple matrix? So remember that U is a unitary means what? U star U is equal to identity is equal to U star. No. That means U is invertible in particular and the inverse is U star. Now that's what I say. So here I'm asking not just invertible, I want to have a unitary matrix. Okay, so why I need this one? So suppose this happens. I know that there exists a nice unitary matrix. I have a unitary matrix U and a nice matrix D such that this happens. Then what happens? If you look at A square, what you will get? This tells me that A square is A into A. So A is U D U star. And again, U D U star, but U is a unitary, so U star U becomes identity. So what you get? U D into D U, that means U D square U star. So if I look at A cube, what happens? A cube will be equal to A square into A. But what is A square? A square is U D square U star into U D U star. Again, U star U is identity. So this gives me U D cube U star. So this tells me that in general, if I start with any K, to compute the power of A, the kth power of A, it's enough to look at the product of these three matrices, U, D to the power K, and U star. Okay, so this tells me that, for example, suppose here D is a diagonal matrix, then what happens? So it's easy to compute the kth power of any power of the diagonal matrix. What you do is that just look at the corresponding power in the each diagonal. That is what you don't have to really multiply the matrix D. No. So for diagonal matrix, it's very easy to compute the k power of the matrix A. So this saying that if I know that if I can write A as something like this, U D U star, where D is a diagonal matrix, then computing the kth power, that means multiplying the k matrix A k times, it's equivalent to multiplying only three matrices. So this drastically reduces the number of computation involved here. Okay, so this is one of the reasons why we have to look at these kind of things. Okay, so now what is it? So this tells you you can take at any power of A. So if I know that this is in this nice form, then you can compute any power of A very easily. What else you can do? You can even do something more. For example, suppose I start with a polynomial P of Z, say AJ, ZJ. Then look at the corresponding polynomial in A. So what is that? By this I mean A naught I, A1. So just Z you replace by the matrix A. So, okay. What is I? I is U star U. And A is U D U star. A square is U D square U star. And A to the power K is U D to the power K U star. So everywhere you have U and U star common, you take that outside. So what you get is that this one. But if I look at this interior portion, that is actually equal to the polynomial of D. So this saying that in fact I can even compute any polynomials in A that is equal to just only multiplying three matrices U and PD U star. Again, look at the PD star. This again you can see that you can easily compute. Just look at the corresponding polynomials in the polynomial values of the diagonal entries. Okay, so this drastically reduces the number of computation involved. Okay, so this is our ultimate aim. So given a matrix, can you get U, a unitary U, and a diagonal, a matrix D such that this matrix is D, symbol such that this happens. We can write it as UD used. Okay, so here is the first thing what you can do. So this is what you know as Schur upper triangulation. So Schur's theorem says that you can always get the matrix D in such a way that the matrix D is an upper triangular matrix. That means given any matrix A, you can get a unitary U such that U star AU is an upper triangular matrix. So if I call this product is equal to D, then it's saying that there exists an upper triangular matrix D and a unitary U such that A is equal to UD U star. So both the things are equivalent. Okay, this theorem. Okay, so let's look at a linear map. So construct a linear map T from Cn to Cn. I define it by this way. T of x is equal to Ax. So remember that x is a linear, it's a column vector, and A is a matrix, and x is again a column vector. So Ax you can multiply. So that again gives you a column vector. Then what I do is that look at the matrix Tx. Okay, so look at the matrix of T with respect to the standard basis. So let me denote it by E. So E1, E2, etc. E and B the standard basis of orthogonal basis for Cn. Then how I compute the matrix of T? That will be the first column will be T of the coordinate vector of T of E1 with respect to E. But what is T of E1? That is equal to A E1. And the second column will be T of E2 with respect to E, but T of E2 is A E2 and so on and so. So you want to get the A E1, A E2, A En, etc. But what about AE1? So this you can easily see that. So you are given a matrix A and your E1 is 1, 0, 0, 0. You can see that if you multiply the matrix A with E, the vector 1, 0, 0, you will get exactly the first column of A. Similarly, if I look at AE2, you will get the second column of A and so on. So AEN will get the last column of A. Now you have vectors in Cn and you are looking at the coordinate vector of that vector with respect to the standard basis. We already saw that we will do the same vector. So that means what? This matrix is equal to the matrix with the first column is equal to the first column of A, second column is equal to second column. That means ultimately, finally, you are getting the same matrix E. Same matrix A. Okay, so what else you can do? So in the last lecture, we saw that given any linear map, we can always get a basis with respect to which the matrix of T will be an upper triangular matrix. Okay, so this you already saw in the last lecture. But that is not good enough for me because I need to get an orthonormal basis. So what you can do is that, so here you are given a basis. So it's a linearly independent set. So you can apply the Gram-Schmidt process to this basis so that you will get an orthonormal basis. Okay, now what is this orthonormal basis has the property? So the resulting orthonormal basis, let me call it as B dash. Okay, so from Vs, you defined B dash. So what is the property you have? So the Gram-Schmidt process tells you that if I look at the span of V1, that is equal to span of U2, and span of V1, V2, that is equal to span of U1, U2. And in general, if I look at span of U1, U2, etc., Uj, that is equal to span of V1, V2, etc., Vj. So this actually follows from the Gram-Schmidt process itself. So note that this Uj is clearly an element here. That means Uj is also an element here. But what that means? Uj is a linear combination of V1, V2, etc., Vj. So if I look at T of Uj, that will be a linear combination of T of V1, etc., T of Vj. That means what? T of Uj belongs to the span of T of V1, etc., T of Vj. Okay, but again, so in the last class you saw that this is a basis, B is a basis with respect to which this matrix T is a upper triangular matrix. You saw some equivalent condition for this matrix. What you saw is that this equivalent saying that T of V1 is an element in a span of V1, T of V2 is an element in span of V1, V2, etc. T of Vj is an element in span of V1, V2, etc. Vj. That means what? Each of the T of Vi is belongs to the span of V1, V2, etc. Vj. That means the entire span is again a subset of it. But that is implied that. But we already saw that these two sets is equal to the span of V1, V2, etc. Uj. So what you got? So you got an orthonormal basis B dash, U1, U2, etc., Un, and it has the property that T of Uj belongs to U1, U2, etc., Uj for all j. And again, from the theorem that you proved in the last class, this last condition is equivalent to saying that the matrix of T with respect to this basis B dash is a upper triangular matrix. Okay, so what you did so far? So you started with this linear map T, then you look at the standard basis E with respect to which you compute the matrix, and we saw that that is equal to A. And then you constructed another orthonormal basis B dash with respect to which we got this matrix is a upper triangular matrix. But we know that when you have two bases and the matrices are associated by this equation that we already saw. Now, from the previous theorem, we know that these matrices are related by this way. So what you got is that U inverse AU is a this matrix, but just now we saw that this matrix is an upper triangular matrix. So what you have to prove? You have to get that U is a unitary such that this is an upper triangular matrix. So we already got that this is an upper triangular matrix, but what is remaining that we don't know whether it's a unitary or not. You got an invertible matrix, that's only we got. But let us try to see what is this matrix U. So by definition, U is the matrix of identity map with respect to the standard basis E and the B dash. Okay, you just go back to the previous slide so that you can understand this how you define the matrix U. But what is this one? You look at elements of B dash, and then you look at the image, then you expand in terms of the standard basis. So the first vector is B dash. So B dash is given to U1, U2, etc. UN. Look at the image of U1, that is U1 itself, and look at the coordinate vector with respect to the standard basis. Similarly, U2 with respect to the standard basis, and so on and so. Okay, sorry, here it is again the E. Okay, but what you know is that given any vector, and if you look at the coordinate vector of that vector with respect to the standard basis, that gives you the same vector. So this gives you U1, this gives you U2, and etc. This gives you U. So what you got is that this U, the matrix U, is actually given by the these vectors U1, U2, etc. UA, or each of the UIs coming from the basis B. So remember that each of the UIs are an element in the C. So each of them is a column vector. But since all these UIs are a orthonormal basis, from the first exercise, what you saw is that this resulting matrix will be a unitary matrix. So what you saw is that here the matrix you got is a unitary matrix. So what you know that U inverse is actually equal to U star. So what you got is that U is a unitary matrix, and so this becomes U star AU, and that is equal to this one, but it is an upper triangular matrix, and that is what we need to prove. Okay, so this what to say. So what to show is that given any linear matrix A, we can always get a unitary U such that U star AU is a upper triangular matrix. So what this tells you in terms of the linear map. So we know that is a remember that we said that T with respect to basis B is symbol means U star A is symbol. So what you got here is that U star AU is a symbol matrix. That means an upper triangular matrix. So if I state this in terms of the linear maps, what that tells you? That tells you the same following. So suppose B is a five-dimensional complex inner product space and T is a linear map. And then this saying that there always exists an ordered orthonormal basis B for B with respect to which the matrix of T is a upper triangular matrix. Okay, so the proof I am leaving it as an exercise. Again, we don't have to prove it. We already did all the computer. Either you can look at the proof of the matrix, from that you can derive it, or otherwise you can use the analog between matrices and linear maps. Okay, so I am not going to do the proof here. Okay, so what we saw is that given any complex matrix here, you can always get a unitary U such that U star A is a upper triangular matrix. So that upper triangular means what? All the entries below the diagonal is a 0 entries. Okay, now here I would like to ask even stronger. So now I'll ask even more strong question. So can you get this unitary U in such a way that U star A is a up diagonal matrix? So is it possible that you can always get this matrix be diagonal? Okay, so let us give some name whenever this happens. So this is what I call it as a unitarily diagonalizable. Okay. So a matrix of A is said to be unitarily diagonalizable if there exists a unitary U such that U star A is a diagonal matrix. So what our aim is to prove that is it true that every matrix is unitarily diagonalizable. But that is not true in general. So what you do is that if that is not true in general, then when that can happen? Okay, so that is what we want to see. So we try to answer this in the reverse order. So what you do that, we assume that suppose the given matrix is unitarily diagnosable. Then what can happen? What are the properties that the matrix A can have? Okay. So what does that mean? So if I know that this is unitarily diagnosable, that means what? U star A, U is a diagonal matrix. So if I call that product is D, then that is equal to saying that A is equal to UD U star for some diagonal D and a unitary U. So then if I look at the product A star, so this gives you UD U star and A star become this one. But again, U is a unitary, so U star U become identity matrix. So what you get is that U, D, D star, U star. But remember that D is a diagonal matrix. So D star is also a diagonal matrix. So two diagonal matrices always commute. So D star will be equal to D star D. Okay. But again, you can see that this is equal to A star A. So what you got? A star is equal to A star A. That means what? A is a normal matrix. So what we saw is that if A is a unitarily diagnosable matrix, then it has to be a normal matrix. There is no other way. So if you start with a non-normal matrix, then you cannot unitarily diagnose it. So this is what it says. So you may ask the converse. So converse, what is the converse? Is it true that suppose you started with a normal matrix? Is it true that it is always unitarily diagonal? So that means can you always get a matrix U, unitary U and a diagonal D such that A is equal to UD used? Okay. The answer is yes, you can do. So in fact, both the conditions are equivalent. So that is what the first theorem says. So okay, so what is the theorem? So you are given a complex matrix, then the following conditions are equivalent. So what is the first condition? First condition saying that A is unitarily diagnosable, and the second condition saying that A is a normal matrix. So how you prove this one? So one implies two, that we already saw now, because unitarily diagnosable implies one. So what you have to prove is the other way. So what you have to do? You are given that A is normal, and you have to prove that A is unitarily diagnosable. Okay, but what we saw just now from the Schur's theorem is that you can always get a unitary U such that U star A U is a upper triangular matrix. So remember that here in the Schur's theorem we use normality. So this is true even for any complex matrix. Now the thing is that if I assume, so if you assume that the second condition too, A is normal, I have to prove that it's unitarily diagnosable. Okay. So what this additional condition A normal implies? Okay. So look at the product of D star. So what is D? D is U star A U, and D star is U star A star U. But again, U star is an identity. So what you get? U star A star U. But we assume that A is a normal matrix. So A star will be equal to A star A. So you can see that this is again equal to D star D. So what that tells you? D star is equal to D star D. So what you get is that D is a normal matrix. So what you observe, so already know that D is a upper triangular matrix. And from here we observe that D is also a normal matrix. So this is a very standard, very basic computation. You can check easily that if you have an upper triangular matrix, then this is normal if and only if it is a diagonal matrix. That you can easily verify. You just write D equal to D11, D12, etc. So you have an upper triangular. So the entries below the diagonals are 0. So you just multiply D and D star, and now you equate the two matrices, D star and D star D, equate the coefficient of each entry. You can see that will imply that only the diagonal entries will be non-zero, all others will be 0. So that means you will get a diagonal matrix, and that is what we need to prove. So this is upper triangular matrix, and a normal implies that D is actually a diagonal matrix. That means A is unitarily diagnosable. Okay, so this is what I got. Okay, so this is saying that whenever I have a normal matrix, I can always unitarily diagnose it. So you may ask, how I get such a matrix? So it's easy to verify. So given any matrix here, you can easily check whether it's normal or not, because you can compute A star and A star here. You can compare them whether they are equal or not. But what is the problem is that how I get the matrix U, D and U star. Okay, so that means given a matrix, normal matrix, how I unitarily diagnose it. That means how I get the matrix U and how I get the matrix D. Okay, so again, I will assume that the first property. So normal means what? It's unitarily diagnosable, that we already know. What I need to get is how I get the matrix U and D. So let us assume A is equal to U, D, U star for some diagonal matrix D and unitarily D. Now we'll try to see what are the properties that U and D satisfy. And from that, you try to get the construct the matrix U and D. Okay, but what does this mean? So now, once you have this one, if I look at determinant of lambda I minus A, where lambda is any complex number, this is equal to this one. So why this one? Because this lambda is a scalar. So U lambda I U star, that gives you lambda I. Then U D U star, that gives you A. So these two determinants are same. But what is this? Determinant of product of three matrices. But that is equal to determinant of the, product of the determinants. But U star is a unitary matrix. So U is a unitary matrix. So U star is U inverse. So you have a determinant of U here and a determinant of U inverse here. So these two will get cancelled. So what is remaining is the determinant of lambda I minus D. Okay. So what this tells you that if I look at the characteristic polynomial of A, that is same as the characteristic polynomial of D. So what does that mean? That means the set of all eigenvalues of A is same as the set of all eigenvalues of D. So this is what it says. So by this sigma of A, I mean the set of all eigenvalues of A. So what you observe that the eigenvalues of A is same as the eigenvalues of D. Yeah. But what about the eigenvalues of a diagonal matrix? You know that is actually the diagonal entries of D. So let us say the diagonal entries are D1, D2, etc., Dn. Okay. So what we saw just now. So if we know that there exists a U and a D, so that A is equal to U, D, U star, then what about the diagonal matrix D? This saying that the diagonal entries of D, that means the D1, D2, etc., Dn, has to be the eigenvalues of A. So there is no other choice. So the diagonal entries has to be the eigenvalues of A. Okay. So this tells you about the matrix D. Now what about the matrix D? Matrix U. Okay. Now let us write U as U1, U2, etc., Un. So where each of the Ui's are the column vectors of U. And then if I look at A equal to U, D, U star, if I multiply both the side with U, what I get is that AU is equal to UD. But what is AU? So you multiply A with this matrix. So you know that is equal to AU1, AU2, etc., AUN. Similarly, you can also see that if I compute UD, that will give me D1U1, D2U2, DNU1. So where D's are numbers. Okay. So these two matrices are equal means what? The corresponding columns are equal. That means what? AUJ is equal to DJUJ for every J. So what that tells you? So remember that U is a unitary matrix. That means the columns form an orthonormal basis. That means what? On orthonormal basis cannot contain zero vector. That means all the Ui's are non-zero vector. So then what this tells you that AUJ is equal to DJUJ implies that UJ is an eigenvector of A associated with the eigenvalue DJ. Okay, so because we already saw that all the DIs are eigenvalues. Now here this is saying that the jth column of U will be a eigenvector of A corresponding to the jth eigenvalue DJ. So it cannot be an arbitrary thing. Okay, so this tells you about the matrix U and D. So the columns U has to be the eigenvectors of A, and the diagonals of D has to be the eigenvalues of D. Okay, but we have something more from here. What you saw here is that this is an orthonormal basis. Okay, so U is a unitary matrix. Then what we know is that U1, U2, etc., UN is a orthonormal basis that we already saw from the first exercise. So what you got is that U1, U2, etc., UN is an orthonormal basis. But what about all the Ui's? All the Ui's are actually eigenvectors. So what you saw is that we started with this condition, A is unitarily diagnosable. Then what we obtained is that there always exists an orthonormal basis Cn consisting of eigenvectors of A. So what are the eigenvectors? This is exactly U1, U2, etc., UD. Okay, so this gives you only one direction. Okay, again, you may ask, what about the converse? Is it true that, suppose I know that I have an orthonormal basis for Cn consisting of eigenvectors of A. Is it true that A is unitarily diagnosable? Okay, so that's what the second theorem says. This is saying that yes, that is true. So saying that the two conditions are equivalent. So what is the first condition? A is unitarily diagnosable. Then there exists an orthonormal basis for Cn consisting of eigenvectors of A. But remember that what was the first theorem? First theorem saying that A is normal if and only if A is unitarily diagnosable. And this theorem saying that A is unitarily diagnosable if and only if there exists an orthogonal basis consisting of Cn, consisting of eigenvectors of A. So all these three conditions are equivalent if I combine both the theorems. Okay. So how I prove this theorem? So 1 implies 2 that we already saw just now. Okay, now how I prove the converse? So what I do? So we are given that there exists an orthogonal basis for Cn consisting of eigenvectors of A. What I need to prove that? I have to prove that A is unitarily diagonalizable. That means what? I have to prove that there exists unitary U and a diagonal matrix D such that A is equal to UD U star. Okay, so how I get this U and D? But we already saw that whenever, if at all there is U and D exists, then what about D? D has to be the eigenvalues, the diagonal entries has to be the eigenvalues of A, and the columns of U has to be eigenvector. So you have a natural choice here. So you are given A, so you just compute all the eigenvalues of A. So you have exactly n eigenvalues here. That you, using that eigenvalues, you construct the matrix D. And what about U? You have to get the columns of U as some eigenvector. But here you are already given some eigenvector, so that you use that eigenvectors to construct the matrix U also. So there is no other choice. So you start with the D equal to the set of all eigenvalues of A. You first compute that one. Then you construct the matrix U is equal to the given orthogonal basis. So you are already given that U1, U2, etc. UN as orthogonal basis consisting of eigenvectors. Okay. So these are orthogonal basis, hence U is a unitary. Now what I have to prove that this U and D satisfy the property that A is equal to UD U star. But that is easy because what I need to prove that AU is equal to UD. No, because U is a unitary. So from here, this follows that A is equal to UD U star. Okay, so then how I prove AU is equal to UD? But what is AU? This is equal to AU1, AU2, etc., AUN. But remember that UIs are eigenvalues, eigenvectors corresponding to the A. Okay, so there is a correction here. This is DI. So AUI is equal to DI UI. So here, what do also AU is equal to AU1, AU2, etc., AUN. So that become equals D1 U1, D2 U2, etc., DN UN. And that gives you that equal to UD. And that's what you need to prove. Okay. So this they have said that you can, this proof actually tells you something more, how to get the matrix U and how to get the matrix D also. Okay, now before going to proceed something else, let me look at a special case. Let me look at a small example, not example, some observation. So suppose you have U and D such that A is equal to UD U star. Okay. Then you write U is equal to U1, U2, etc., U7. Okay, so I'm considering a 7 by 7 matrix. Then and D is equal to diagonal matrix D1, D2, etc., D7. Okay, so whatever this diagonal entries, we know that whenever this equation holds, then this diagonal entries are the eigenvalues of A. But it may happen that some of the eigenvalues are equal. No, it's not necessarily always that all the eigenvalues are distinct. That may not happen. So for example, suppose D1 and D3 are equal. So the common value are denoted by lambda 1. And suppose that D2, D5, D7, they are also equal. So the common value are denoted by lambda 2. Now D4 equal to lambda 3 and D6 equal to lambda 4. That means no other eigenvalues are same. So only these things are equal. So then what this tells you that if I look at lambda 1, lambda 2, lambda 3, lambda 4, they actually represent the distinct eigenvalues of A. Okay, now what I do is that I construct a new matrix U tilde. So what so see, remember that here D1 and D3 are the same. So what I'll do, I'll look at the corresponding columns U1 and U3. That I'll write it together, U1 and U3. Now here D2, D5, D7, they are actually equal. So I look at the corresponding column U2, U5, U7. That also I'll write it together. And D4 and DC, they are different. So I'll just write U6, U4. So what I get is that I got the matrix U tilde. Again, they are actually coming from the matrix U. But what I did, I just simply change the order of the column. That's the only thing I did. Okay. Now I construct a new diagonal matrix D tilde. So what I do, see here D1 and D3 are the same. So that I write it together. So this is my D1, this is my D3. So but D1, D3 I already denoted by lambda 1. Now D2, D5, D7, that also I write it together, but that is equal to what? Lambda 2, lambda 2, lambda 3. Sorry, lambda 2. Then you have D4 and DC, that I write it here. Okay, so remember that the order is very important here. Okay. Now, now look at U tilde. So U tilde are actually coming from the this column vectors Ui's, but we know that U is a unitary matrix. So the column form an orthogonal basis. So again, that means these vectors are also orthogonal basis. That means what? U tilde is again a unitary matrix. Now, if I compute A U tilde, what you get? This gives me AU1, AU3, AU2, etc. But what is my AU1? This is D1U1, AU3 is D3U3, and so on and so on. But D1U1, D1 is lambda 1 U1, D3 is again lambda 1 U3, D2U2 is lambda 2 U2, D5U3, lambda 2 U5, and so on and so on. So what you get, you are multiplying U1, U3, U2, everything with the scalars lambda 1, lambda 2, etc. So you can easily, again, you can verify that this matrix is actually equal to U tilde, D tilde. So remember that U tilde is a unitary matrix. So this implies that A is equal to U tilde, D tilde, U star, U tilde star. So what we saw here is that, you wrote A as a product of matrix like U tilde, D tilde, U star. Again, U tilde is a unitary matrix, D tilde is a diagonal matrix. But what is important here is that what you observe that the matrix D, if I look at the matrix of D tilde, those entries which are equal, everything I club together. No. So this saying that if A is not, you can always get unitary U and the diagonal matrix D, so U, D, U star, of D, you can club together. If it is not true, then what do you do the same procedure? You just change the order of the columns and also the order of the diagonal entries in D. Okay, so this you can always do. Okay. So once you have this one, what you can get? Okay, now we are in this setup. Suppose A is a normal matrix, then we know that it's unitarily diagonalizable. That means what? There exists a unitary U, so that U star A U is a diagonal matrix. So let us call D1, D2, etc. Di. And we know that this Di has to be eigenvalues of A. There is no other choice. Okay, now let us, from this D1, D2, etc., we said that they may not be equal. So some of them can be equal. So what you do is that from this one, you look at the distinct entries from here. So let us divide by lambda 1, lambda 2, etc., lambda r. So the r will be less than or equal to n with the distinct eigenvalues of A. Then as above, by interchanging the columns of U, that means reordering the base, orthogonal basis, we can assume that U star AU, I can get this D in this form. So what about each? So what you do is that here is lambda 1, and lambda 2, lambda 2, lambda 2, lambda 3, lambda 3, etc. That means same entries, I write it together. That means here this is a diagonal matrix. Each of the DI is a diagonal matrix, which is of the same of this form. So where you have the same lambda j's. Okay, it will be of some size nj. So now what is this one? So now U star AU. So we know that D1, D2, etc. Dr. This you write it as sum of these matrices D1. This is 0, bigger diagonal 0 matrix. Okay, so write it as this sum. Okay, 0, D2, etc. 0, 0, 0, D2. So remember each 0, by this I mean a diagonal 0 matrix of some size. The first one is of size n1, the second one is n2, n3, like that. Okay, that actually n1, n2 comes from here. Okay, but what about each D1? Each Dj is equal to lambda j identity nj. No. So that means this I can simplify. This equal to lambda 1 in1 0 0 0. This becomes lambda 2 0 in2 0 0, etc. Lambda r 0 0 in r. So this is what I get. So U is a unitary. So if I multiply left hand this equation from left hand side by U and right hand side by U star, what I get is that A is equal to lambda 1 U, this matrix U star, lambda 2 U, this matrix U star, and so on and so on. So this is what I get. A is equal to lambda 1 U and Tn1 0 0 U star, this one. Okay. Now let me give some name for these matrices. So U is a matrix. This again another matrix U star. So this entire thing U, this diagonal matrix U star, I'll call it as P1. Similarly U, this diagonal matrix U star, I'll call it as P2, and this last part I'll call it as Pn. So I wrote A is equal to lambda 1 P1 plus lambda 2 P2, etc. lambda r Pr. Okay. So remember that U is a matrix of n by n size. This also n by n. So P1, P2, etc. all are matrices. But what about the matrices? What are the property these matrices have? Okay. So you can easily verify that each Pj is equal to Pj. That is clear because if I look at the star of this matrix, that becomes U the star of this diagonal matrix that is equal to the same thing, because only entries are 1, 1 and 0, 0, 0. Okay, so that gives me the same matrix. And if I look at the square, that again gives me the same, because this matrix U star, again this matrix U star. U star U become identity, and this diagonal matrix, when you multiply twice, you get again the same thing. That means you are getting the same thing. So what about the matrix P1, P2, etc., PR? They are actually orthogonal projection. Now, whenever this condition holds, such matrices are called orthogonal projections. And you can ask one more property here. If I look at the product of Pj with the Pk, so for example, look at P1 into P2. So what I get? U, this diagonal matrix U star, plus U into this diagonal matrix into U star. But U star U will get cancelled, that become identity. Then you have this diagonal matrix into this diagonal matrix. But here you have everything 1, but here everything 0. So when I multiply, this becomes 0. And here you have everything 0, you have 1 everywhere here. So this again becomes 0, and the rest of the entries are 0. So what I get is that P1 into P2 is equal to 0. So similarly, you can prove that if I start with any Pj and Pk, if I take that product, when j not equal to k, this product will become 0. Okay, so, and okay, not only that, if I look at the summation of all these Pj, so remember that P1 is U, this matrix U star. So everywhere you have a U star on the left and right out common. So you just take that outside. So what is remaining? You have this diagonal matrix plus this diagonal matrix plus this. But here is everywhere 1, 1, 1. Rest of the thing 0. But here 0, 0, 1, 1, 1, again 0, 0. So when I add all these things, you will get the n by n matrix with all the diagonal entries 1, 1, 1. That means you are getting the identity matrix. So what you get? U into identity matrix into U star. That means U star. But U is a unitary. That tells you that it is equal to the identity matrix itself. Okay. So what we saw so far. So what we started with? We started with A is a normal matrix. Then we proved that then A, I can write it as sum of a linear combination of P1, P2, etc., PR, where each PA are orthogonal projection, and this projection has some additional property. That means Pj, Pk equal to 0, and summation Pj is equal to I. And this is what we just proved. Okay, so this is what I know. So A normal implies this happens. Okay. As in the earlier case, you may ask, what about the converse? Is it true that suppose I write A as a linear combination of orthogonal projection like this, where projections are this property. Is it true that this resulting matrix A is a normal matrix? Okay. And again, the next theorem says that yes, that is actually true. Okay. So the third theorem saying that suppose you are given a matrix, then these two conditions equivalent. A is normal if and only if you can write A is equal to lambda 1 P1 etc. lambda 2 etc. lambda r PR, where lambda is are the distinct eigenvalues of A and the PIs are orthogonal projection with these two conditions. Okay. So 1 implies 2 we already saw just now. Okay. So what do you have to prove? That the converse. Okay. So what is the converse? So you are given that A is equal to this sum, and then we have to prove that A is a normal matrix. That means what? We have to prove that A star A is equal to A star. Okay. So you just consider A star A. What is A star? A is equal to lambda 1 P1 etc. lambda r PR, the whole star, plus lambda 1 P1 etc. lambda r PR. But what about the star? So all the lambdas are scalars and the PIs are matrices. So this becomes lambda 1 bar P1 star, lambda 2 bar P2 star, etc. lambda r bar PR star. But remember that here given that all the projections are orthogonal projection. That means what? P1 star is equal to P1, P2 star is equal to again P2, PR star is equal to PR. So when you multiply all these things, what you get is this one. Summation over lambda j bar, lambda k, pj, pk. But again, we are given the additional condition that the projection pj, pk equal to 0 whenever j not equal to k. So that means in this sum, whenever j not equal to k, this becomes 0. So only the 1 will be remaining when j equal to k. That means this entire sum reduces to one sum. So you get lambda j bar, lambda j, pj. But what about lambda, this one? This is equal to mod lambda j square, pj. Okay, again remember that when j equal to k, pj, pk will be pj square, and that is equal to pj. That is what I got it here. Okay, so you got that A star A is equal to this sum. Similarly, you can prove that A star also you can compute, you can prove that also equal to the same sum. So what you observe is that A is a normal matrix. So what we saw. So in the first theorem saying that A is normal if and only if it's unitarily diagonalizable. And the second theorem says that A is unitarily diagonalizable if and only if there exists an orthonormal basis consisting of eigenvectors. And the third theorem saying that A is normal if and only if I can write A as a linear combination of projection. So from theorem 1, 2, 3, all these four conditions are equivalent. So when you write all these conditions together, I'll call that as the spectral theorem. Okay, so before that, there is a small exercise. So remember that here, Pj are projections. So there you can think of it as a linear maps or the matrices. You can say whatever the range of Pj's. Okay, so I will just see if I look at all these conditions together, that is what I call the spectral theorem for normal matrices. Okay, so what I need to do. So you started with the matrices A and look at all lambda 1, lambda 2. They are the distinct eigenvalues of A. Then the following conditions are equivalent. So what is the first condition? A is normal if and only if A is diagonalizable, unitarily diagonalizable. That we already saw from theorem 1. And what is the third condition saying that there exists an orthonormal basis consisting of eigenvectors of A. So that is coming from the second theorem. And just now we proved that this again equal to saying that there exists projections, orthonormal projection, such that A you can write it as a linear combination of this projection, where each scalar is coming from the distinct eigenvalues of A. Okay, now there is one more additional condition here which we did not prove. So this saying that if I look at the Cn, then I can write the entire vector space Cn as a direct sum of all these null spaces. So what is this one? Null space of A minus lambda 1. So this is what you call the eigenspace corresponding to lambda 1. This is the eigenspace corresponding to lambda 2, etc. The eigenspace corresponding to lambda 2. So this is saying that the entire vector space Cn, I can write it as the direct sum of the eigenspaces. But there is one more symbol here. Look at here. There is a perp symbol here. So what does it mean? It's not just that they are direct sum. I am saying that they are actually orthogonal direct sum. Okay. So what I mean by orthogonal direct sum? So I hope that in the last class you learned the notion of direct sum. So what do you mean by direct sum? Given any vector here in Cn, I can write it as a sum some x1 plus x2 plus etc. xr, where each xi coming from this corresponding space, x1 coming from the first space, x2 coming from the second, and xn coming from this one. Okay, but when I say this orthogonal direct sum, that means if I start with an element here in this subspace and another vector from this one, the inner product will be 0. Similarly, if I look at a vector from here and a vector from another component, that inner product also becomes 0. That is what I mean by orthogonal direct sum. Okay, so this proof one implies 2 implies 4 that we already proved. Now, so what is remaining that how I prove the fifth condition? Okay, so look at here this decomposition. So let us look at any vector from this one. What did that mean? So suppose I have a vector from here. That means say x. So that means what? Ax minus lambda 1x is equal to 0. That means what? Ax is equal to lambda 1x. That means what? X is an eigenvector corresponding to the coefficient lambda 1. Okay. And similarly, if I look at any from here, that will be an eigenvector corresponding to lambda 2. That means every vector here is an eigenvector. Now, what I know is that suppose this fifth condition happens, then what that means? If I look at any x, any vector from here, that I can write it as a sum of vectors from here. That means what? Each of the vector is an eigenvector. That means any vector I can write it as a linear combination of eigenvector. That means this vector spans the entire thing. So that is what actually this does, the third condition says. And similarly, I can do the other way also. If I start with an orthogonal basis consisting of eigenvector, that means what? Any vector from this orthogonal basis belongs to one of these eigenspace. Okay. Then use the fact that this is an orthogonal basis. That tells me that any vector I can write it as a linear combination of this vector. But each of the vector belongs to one of this sum. That means any vector I write it as a sum of these vectors from this one. So that means they are direct sum. But this is an orthogonal basis. That means if I look at the inner product of two vectors coming from two distinct vectors, they become 0. That tells me that the associated inner product is also this direct sum is an orthogonal direct sum. Okay, there is some computation involved. Okay, and I am not going to do the details right now. So that I am doing it as an exercise. Okay, so this is what this equivalence of all these 5 conditions I prefer to call it as the spectral theorem. Okay, now so this for the matrices. So remember that whenever I have a result for matrices, it always has an analog in the linear vector space. That means for a linear operator, you have an analog result. So what will be the analog result for the linear operator? So what will be the first how to state that theorem? So you start with the matrix here. So that means you have to start with the linear operator in a vector space. Then you can start with the distinct eigenvalues. But then what will be the first condition? A is normal. That should imply that the vector T is something called normal. But then we have not defined what is that normal means. Then here A is unitarily diagonalizable. That means what? A is equal to UD U star. Where D is a diagonal. In other words, this is saying that U star AU is a diagonal matrix. So we saw that is equal to saying that there is a basis, so with respect to which the map T has a diagonal matrix. And the third condition, again, you can state even for linear maps. Similarly, the fourth condition and fifth condition also you can have an analog. Okay, so only problem here what we face is that what you replace by this normal condition here when you want to state the spectral theorem for normal linear operators. Okay. So that's what I'll define it here. So we are given a financial complex in a product space, so that you can always start with the basis B. So then we know that we have this bijective linear map. That means given any T, you can always get a matrix A, which is given by this way. But remember that whenever I have a matrix A, I also have an associated matrix called A star. Okay, but this A star is again a matrix. But since this map is a bijective map, this A star also has a pre-image here. So what is that pre-image? Okay, so since this is a bijective map, we know that this map is a unique element here. So that unique pre-image, I'll call it as the adjoint of the matrix T, and that I'll denote by T star. Okay, so this is the definition. So given a T, there exists a unique operator denoted by T star such that the matrix of T star is equal to exactly A star. That means the star of the matrix of T. So this unique operator T star is called the adjoint of T. Okay. But there is a slight problem here in this definition, because how I get this T star, I fix a basis, then I look at the T and I go construct the matrix of T with respect to this basis, look at the star and coming back. But this definition involves the basis. So you may ask whether this definition will depend upon the basis. But that actually, that's not true. Because you can see that this definition of T star is actually independent of the choice of B. In fact, we do not look at these matrices. In fact, you can directly define the existence of this T star. So by this theorem. So this saying that suppose you have a linear map T, then this T star is the unique linear operator satisfying this inner product property. That means T inner product of TU with the B is equal to inner product of U with the T star V for all U and V. So this is actually the way how you define. Without even looking at the matrices, you can define the linear map T star using this property. Again, from here it's not clear what is T star and why that T star exists. But there need some more tools to prove this one. So I want to say that without looking at the matrix, from this inner product property, you can uniquely determine or define this matrix, this linear operator T star. Okay, so that's what I want to make a comment here. Okay, now you given any matrix linear operator T, you have an associated linear operator T star. Okay, now again, as in the case of matrices, you can ask what are the properties T and T star satisfy, whether T and T star are the same linear map or whether they commute and all these things, and if they what about their product and everything. And depending upon that property, you can classify these linear operators also. Okay, so I look at only one definition. So I'll say that an operator T is said to be normal if T star is equal to T star. This is exactly in the case of matrices. Now remember that matrix also we define the same normal matrices. So I'll say that a map operator is normal if this condition happens. Now we have a meaning for the normal linear operators. Okay. Now once you have that one, we can state the spectral theorem for normal operators. Okay, so what is the spectral theorem tells you? This tells me the following thing. So let V be a financial complex in a product space and T is a linear map. then the first condition is exactly as in the case of matrices, T is normal. And we saw that the second condition in the matrix case, it was A is unitarily diagonalizable. That means what? U star AU is a diagonal matrix. And we saw that that is equal to saying that there exists an orthogonal basis, say B, such that the matrix of T with respect to that basis is a diagonal matrix. And the third, fourth, and fifth condition are exactly the same. But the only thing that in the fifth condition, in the matrix case, we have Cn, but here we have V, the linear vector space V. So I'm saying that this you can write it as a linear combination of, orthogonal direct sum of the corresponding eigen spaces. Okay, so the proof I'm not going to do. Again, I'm doing as exercise. You don't have enough time to do all these things. Again, you can see that either you can look at the proof of the matrix and from that you can prove the same way, or otherwise you use the equivalence of the association, the matrices and the linear map. From that also you can derive it. Okay. So this is what I prefer to call it as the spectral theorem. Okay, now let me just look at here. So what is the second condition? The second condition saying that given any linear map T, I can always get a matrix B such that the TBB is a diagonal. So that is possible if and only if the matrix is a normal matrix. So you may ask, what about general case? If it is normal, what is the best thing that you can do? So what you can see in the second case, what you do is that here in the both the place, domain and codomain place, you are taking the same basis B. No, that is what TB means. B, so TB means TBBB. But what you can do is that in general, instead of if you forget about the single basis B, if you start with the two bases B and B dash, suppose both are orthogonal sum, then also orthogonal basis, then also I can look at the corresponding matrix. Okay, what you see is that in general, if I start with any linear map, if I don't demand that I want to take the same basis, if I am allowed to take two orthogonal bases here, then you can see that you can choose different bases, one here and one other here, so that if I look at the corresponding matrix, you can see that that will become a diagonal matrix. You can choose such a appropriate orthogonal basis. Okay, so this is something what leads to something called a singular value decomposition. So here we demand that both the bases are the same. So if you are allowed to take distinct orthogonal bases, then you can see that you can get a same situation. I mean, you can get a diagonal matrix. Now again, the fourth condition. Look at the fifth condition. So this saying that the entire vector space, I can write it as a orthogonal direct sum of eigenspaces. But you may ask, what about in general? So again, this fifth condition is that this is possible if and only if T is normal. So if T is not normal, what happens? Then look at here. So if look at the right hand side, you can see that all the eigenspaces are subspaces of V. So this, if I look at the direct sum, that is also a subspace of V. So the orthogonal direct sum is again a subspace of V. So in general, it may not happen that all these direct sum become the full space. So it can be the case that it will be a proper subspace. So if I am to get a similar way, if I am to have a decompose this V into orthogonal direct sum of some spaces, so what is the best way that you can do? So here is saying that just looking at null spaces are not good enough. So there it comes up the notion of a generalized eigenvector. So remember that here every element in this subspaces are eigenvectors. So if I allow to take generalized eigenvectors, then you can see that the entire vector space you can decompose as the eigenspace, the generalized eigenspaces. Okay, so that is something what you see in the next lecture. In the singular value decomposition, for example, the analog of condition 2, that you will see again in the next lecture. Okay, so I think the time is almost up. So maybe I don't have enough time to do anything more. So I thought I'll give an example. So maybe I'll quickly go through it. So start with the matrix A. Okay, so this you can see that it's actually a normal matrix that you can easily verify. So that tells me that I can unitarily diagonalize it. I can get orthonormal basis consisting of eigenvectors, and also I can write it as a linear combination of projections. So how I get all these things? So how I get the unitarily diagonalization? So for that I have to compute the eigenvalues of A first. You can see that the eigenvalues are 0, 0, 3. So this, if I count D1, D2, D3, this is my diagonal matrix D. Okay. Now I want to compute the unitary matrix U. So how I compute the unitary matrix? Remember that we saw that the unitary matrix U should contain, the column should be eigenvectors corresponding to the eigenvalue. So how I compute the eigenvector? That means look at each eigenvalue. So look at the distinct eigenvalue 0 and 3. So look at the null space. So this is my eigenspace. So look at this space. You can compute that this actually equal to span of these two vectors. Okay, but this is not from an orthonormal basis. So what you do that you apply Gram-Schmidt process to these two vectors. Then you get U1 and U2. So that this become an orthonormal basis. So what I tend to do is that for each eigenspace, you apply, for each eigenspace, you compute an orthonormal basis. Then the union of these two, all these orthonormal bases gives the your required orthonormal basis. Okay. So this U1, U2 gives an orthonormal basis for the first eigenspace. Similarly, look at the second eigenvalue 3 and look at the null space of 3. That means the eigenspace of 3. You can see that that is equal to span of this vector. But again, this is not a unit vector. So I have to get an orthonormal basis. So I look at U3, then this format orthonormal basis. So how many vectors I got? I got U1, U2, U3. No, so I got 3 orthonormal vectors. So 3 vectors which are eigenvectors. So you got 3 vectors, U1, U2, U3, U3. And all these vectors, you can see that they are linearly independent. In fact, they form an orthonormal basis. Okay, so this is your orthonormal basis consisting of eigenvectors. And if I look at the diagonalization, you take a D equal to the diagonal matrix 0, 0, 3. And the matrix U, you look at the corresponding. So corresponding to 0, you have 0 occurring twice. So you have 2 eigenvectors corresponding to U1 and U2. And corresponding to 3, you have 1 unit. So you have to write in the same order. Then you can see that U is a unitary. And this UD and U satisfy this equation. A is equal to UD, U star. And again, if you want to compute the projection, I don't have time to explain how I compute the projection, but you can see that if I define P1 is equal to this matrix and the P2 is equal to this matrix, you can see that all these P1 and P2 are orthogonal projections. That means these conditions satisfy P1, P2 equal to 0, P2, P1 equal to 0, and the sum is again equal to 1. And finally, you can see that A is the sum of lambda 1 P1 plus lambda 2 P2, where lambda 1 is 0 and lambda 2 is 3. Okay, so this is what all I want to say about the spectral theorem. Okay, so maybe let me stop it here also, because I thought maybe I'll give some more example and some consequence. I don't have enough time to do that, so maybe I'll stop it here. Okay, so this is the reference. So I think also this workshop mainly following the first textbook, and you can also refer this next to this textbook by Mayer and Cohn and Johnson. And also a part of this lecture is also influenced by the lectures by Professor Raja Rambat from ISA Bangalore. Okay. So with that, I'll stop it here. Okay, thank you all.
Thank you, sir. Any questions?